It's a pleasure. I'm Stephan. You may know me from the Julia user group Munich as well. I'm organizing this too, inviting a speaker every other month and giving another introductory talk myself. So you're invited to join this as well. We're going to stay online also for a bit while we also get some in-person meetups in Munich. I'm going to speak to you about some expression parsing. This is actually a quite old package of mine, which I used to build up the where trades package. So this will be the running example. Maybe short words about Jolin. So Jolin.io tries to kind of spread Julia really in Central Europe. I'm based in Munich in Germany. And I hope to get a broader community out in kind of mainstream industry, more focusing on data science. And you're welcome to check out cloud.jolin.io, where this kind of first entry-level product, hosted on jolin.io. Okay, so let's start. I have 3 little parts for today's outline. The second one is a really big overview slide. We'll go into detail. But first, some introduction to what this package of mine, ExprParsers, actually is about. And then we'll compare it to different ways, how you actually can go on and do your little macro. There are a couple of ways by now in Julia, and I hope I built a really great little applied comparison. We will see some code on there. And the last remark kind of on some details that you can also kind of, if you go the expression parsers route, you can also easily extend this. Okay, so what is expression parsers about? So the idea is like, I have a goal in mind if I want to build my macro, and there it may come natural to you, it came to me, to first build a kind of parser, so to define which kind of syntax you actually want to grasp. And it's usually, if you build a macro, it's usually something different from normal Julia syntax. So it really makes sense kind of to have, in case, a really nested approach and build it on your own so that you really define what you want to support. Then second step is you have this parser readily defined. You use this parse expression function and you get a parsed object back. So there's really kind of a distinction between parsers and parsed objects. You can mutate then everything which you get, so it's a real object which you can deal with. And if you're done, you use the second function toExpression, and you get a normal proper expression back. So this is the workflow I'm using, and so this is how this is built for. Let's take a look at some concrete code. So this is how it looks like. Let's take this little feature and zoom in a bit. We start by, of course, using expression parsers. I skipped over this apparently. It gives you access to a little constant, the EP. I prefer this quite a lot because there are a lot of types which you use, and coming from Python, this feels also natural to have kind of a short abbreviation, and makes the code more concise. And this is really just there as soon as you type using expression parsers. This abbreviation will be in your namespace. So we define then in this example a little parser which parses type ranges. They're the name, so they occur in where statements. But you can also really just find them in normal Julia code. And you see we have kind of a little extra using the normal call. We can now kind of with all these parsers define the sub-parsers for the given parts. So in this case, we say a name should only be parsed if this is actually a symbol. And we could take a look at the output. You see that it defaults actually to have a check on whether this is type of an any. This is a type, checks just whether it's an instance of the given type. And for our name, we now have our special check that we really only accept symbols. Okay, so then you parse this, you give in your expression, and you see that it will fail if the given part does not match. So in here, really 1, 2, 3 is not passed as a symbol, but this is a literal value, and hence it will fail. So this is a conceived example, but you can imagine now you really have your custom support and you can build it right into the parser. Yeah, so this gives you a check. So what you get back then is really also a well-typed object. If it succeeds, you get the type range with the underscore parsed, and this is, every other parser follows the same pattern. They are defined always in this twin setup. You have a parser and you have the parsed object. And for simplicity, there's not another module collecting all the parsed objects, but it's really on the same namespace, simplifying access, but with this underscore parsed. And you see, we get it, and we kind of also get these extra parts, and this is kind of the reason also why this is there. So I named this talk Object Orientation for Macros, and that is like you have in Julia many ways to kind of represent similar things. The most common, which you think of, is functions. Yeah, you have this multi-line function syntax, and you have the one-liner, and they are different syntax for the very same thing. And also here, having a type range, we also have different syntax. We have kind of the smaller one, we have the bigger one, we have kind of the real in-between range, and they are all kind of the same as like a type range. And this is now, summarizing it for this part. So we get the lower bound, which is then defaulting to union, the empty union, as you know. And if we would have defined it the other way around, then the upper bound would default to any. So this is there for your convenience. This is really a type range in a semantic sense. You don't need to care about the precise syntax which was used. This is then passed for you. So this is the intention of this package, to make this into a reusable component. We can also change it afterwards. So while the parser is actually immutable, which makes sense for constructing a parser. To be safe, this is really the parser you want. The parsed object then is mutable. You can change it after the fact, which is usually also what you want to do. And then, reconstruct whatever your macro wants to do. Okay, so this is my little intro to kind of what's the flair of the package. And now, some more overview first before we get into one example comparing it with other approaches. So this is just an overview, what is all there. So we have some basics, like this is all object orientated. So we have kind of an extra type for all of this, which is handy for then some dispatch, Julia dispatch. So, but there's kind of general support. If you only have a predicate, you can wrap it into satisfies predicate. We have this is which we used already, and these two extra constants, anything or any symbol, used quite a lot in my code. But we have then also kind of these standard expressions, like a function, and breaking down the function, there's this, a parser for signature, for call, for an argument. This is also a very complex thing in Julia. There are quite a couple of ways to represent an argument in the expression tree. And we have assignment and so forth. So there may probably be something missing. Actually, having looking more into it, I already spot that the if-else is currently not represented. It just didn't pop up for my case. So as usual, you forget about something. So this would be a natural addition, And there may be other parts in Julia. But if-else is probably going to be added soon here. There are some meta parsers which are quite neat. The most important is probably the any-of. So just the or concatenation of the parsers. The first one which parses correctly gets the hit and is returned. And because it's all kind of object-oriented, you have this type information which captures which parser actually hit. So you then use just normal Julia dispatch and you're ready to go. So very handy, but for completeness, there's all of, similarly. And there's a special macro because sometimes you have some complex thing and reuse kind of a type range for the one and for the other part. And there's a little wrapper named, which you can give a tag. Just like, in Julia, we can use this as part of the type. And so, this is just kind of a helper type surrounding it if you have some more complex stuff. And if the passed result will then also be wrapped here, so you can dispatch on your custom name tag. that was handy if you have kind of similar structures, a type range for the one and type range for the other. We're going to see that. There's a very special one for creating kind of really complex parsers. You have kind of a lot of nested parsers, or you may have, and then it's handy kind of to collect the key things which you are interested in at the top level. And this is what this meta parser is for. Yeah, it gives you an interface how you can easily define your nested structure while collecting the results on the top dictionary. So you see here, this thing is constructed by using a do index with an anonymous function. And this dictionary is then really used kind of as the final one. And instead of just assigning the name, I now do a double assignment. I assign it to the name and I assign it to this anonymous dictionary. And yeah, this will then be used by the machinery to really give you access on the parser itself, to access the parsers, the subparsers. And if you parsed it, then you will, on the parsed object, you will also have the ability to access these subparts. That's quite neat. You can also change it as you see it. So this is all taken care of. And okay, so this was not so easy. And yeah, zooming a bit below, then this also works. Like it's really kind of taken care of that this sub-indexing works out well. So this is useful for constructing really complex parsers, and yeah, and makes it kind of also nicely complete. Okay, great. Then I want to go on to do some comparisons, and yeah, we have also enough time left. So there are by now a couple of packages out there. Macro Tools is the go-to package, which kind of most of you may know of if you did some macro stuff. But there are also others. ExprParsers.jl, there was a talk on the conference already about it with ExprParsers or ExprParsers Lite. This kind of a new kid on the block, far newer than actually expression parsers. I just haven't found the time to announce it in some way on JuliaCon. But they are different. So a little tiny table comparison here. So ExprParsers and ML style, we're going to see it. They are kind of related. They're building on top of the same pattern matching machinery, where ExprParsers just defines a couple of extra helpers. We're going to see them in action. I first note the ExprParsers and ML style. They have a far larger ecosystem on pattern matching in general, building on what is called algebraic data types. And I'm not going to go into the details here. I'm just focusing on what is related to expression parsing. Okay, the example I want to compare is actually the syntax you find in another package of mine, the where traits. And this gives you access kind of to, let's say nested dispatch or traits like dispatch in a simple way. And let's again zoom in here. So we have a function like this. We can annotate with the traits macro, and then we can extend what we can write in the where part of it to really use function expressions. And use actually arbitrary functions, but also like these interface functions. And there are now kind of three things which we want to extract. And so dispatch on functions, which just return some value, like a Boolean usually in this regard. Dispatch on function, which return anything. Then we have kind of this is a check here, whether it's of the subtype, or we can check on upper bounds. These are three cases which actually are separately handled. And I show now this little example how you would kind of extract all these three cases. All these three cases from this example expression. So tiny part, but we have some complexity in it. We have a type variable here, which we reuse in one of the function calls. We have also type variable being reused as an upper bound. So Julia actually allows for quite complex expressions. It's really, I think one of the reasons, or one of the design decisions Julia went with, to not be a set of parentheses like Lisp, but support more natural syntax. But this then gets quite complex. Okay, so this is the main last slide in the sense, or yeah, we're going to spend a little time here. These are the 4 packages and how you would do it with them. So I have macro tools here first, probably then going to expression parsers and then looking at JuliaCon Lite and ML style. So let's focus on macro tools. So if we do the standard way, we actually have a lot of support. If you have looked into it, yeah, we have a special function which is there to really get rid of this distinction between multi-line functions and a single-line function. It's the only support for something like this, but there is it. Yeah, macrotools.splitDef is a specific function for exactly this use case. So here, yeah, that's just enough. We have then the function definition, which has per dictionary index gives us access to kind of subparts of it. And here we are interested in the where statements. And then macro tools also has a nice capture macro, which is twofold. Yeah, it on the one side has this inline syntax, which you can use to extract information. We are actually not using this right now, but yeah, so a call variable would be defined now and an args variable would be defined now, which you can really access in here. But we are actually only interested whether this matches or not. And this is kind of given by capture returning a Boolean, whether it was successful or not. And yeah, we do this. And if we match kind of one of these syntaxes, which I showed you, just the plain call or the type check, or the subtype check, then we put it into the respective part. So it's really just a tiny example. We return them, and yeah, okay, we did it. So this is a way you would do it kind of with standard macro tools, which I find is actually pretty neat. But yeah, the support for more complex objects is actually really restricted to the function itself. And if you have other parts which you would like to abstract away, this is not so much your package. It really rather goes this functional style and with this macro to extract things given really standard Julia syntax, where you again need to be careful about getting all the different ways of writing it. Okay, so using the expression parser, things look like this. I usually combine it with another tiny package of mine, the simple match. We're going to see it in a second. But the approach now is kind of to first define the parser. Yeah, this is kind of another kind of mentality. And this is a bit of complex parser, so it combines a couple of ones. We have a call parser. We have a special type range, which checks that the actual thing which is there in the type range is really a call. And we have a normal type range, a type annotation, and some fallback for just an arbitrary symbol. And as you see also, I'm using this special named meta macro to make my life simpler for the dispatch part. So because I now have used 2 type ranges here, I want to have a bit better type support. And what I do then is that I have my this is the function definition. I already parsed it. I skimmed over this. So I have 2 parsers. I'm sorry for being too fast on this one. So the function definition I already parsed with the plain function definition. And then I have an extra parser for the where statements. So really going into detail there. And I'm just moving over the wheres and the function definitions. So you could kind of combine this together. Yeah, it's kind of like you want to do it. We could also have built a big function definition parser, yeah, and do it that way. It's a bit like, depending on your case and on your style, we can also kind of really just do it 2 steps and have 1 parser in the first step and a second parser in the second step. And this is what we're doing here. Then looping over all the wheres also rather matches the other example. And what we do now is that we use this little match here, which has an inline function dispatch, but it's really just a normal function dispatch where you just don't have to care about the function name. So we parse it. And then, for the different cases, we really just use normal type dispatch. So super simple. You can also put this into another function somewhere else. This might be a complex logic. You don't have to put it here. It's really just standard function dispatch. and we then have these cases separated and collect them. Yeah, and finally, in this case, we again call to expression because you have a more complex representation. And yeah, final goal might be to have some expressions. But of course, yeah, in between, you rather work on the object representation. Okay, let's check the time. Yep. Okay, so ExprParsers comes in different flavors, but actually, so yeah, summary, the ExprParsers Lite version, which is actually a real performant package, it does not give you much because it actually relies on the ML style package later on. So what you see here actually that it gives you again a function parser in a sense, or a thing to work with functions in an object way. And yeah, so we can extract this definition, but this is actually it already, what we can use for this case. And all the other code is actually in base. So this is nothing special to ExprParsers Lite, but this part here, having the for loop over the where statements, this is really just standard base, which is also awesome. In meta.isExpression, you have a very common macro which you use. If you haven't seen this kind of really standard, helpful to check that this is an expression with the respective head. And with something like this, we can also kind of use standard base to get this. Again, here the difficulty lies in really kind of making sure that you have all the cases covered. Yeah, all the different syntax options which Julia support, you also need to support in this macro. So that's always the disadvantage of going kind of the normal expression way instead of, that's the advantage of expression parsers, that you have this object orientation thinking, that you don't need to care about these details. Okay, last part, which is, I think, really interesting, is to see ML style working if you haven't done so. So ML style is really basic, just there for pattern matching in a generic way, and also you are supporting expressions. So there's in ML style, there's kind of no object part to represent a function. You really would have to make sure also on this layer that you do everything right. But of course, you can combine it with others. That's kind of for exemplary purposes. This is how it works. We have a completely different match macro. This is really coming from ML style. And yeah, so we can then put in just standard expressions and extract things of it by having kind of a interpolation syntax as well. And with this little pair symbol, we have all the rules set up. But again, you need to make sure you're now really getting all the rules. So these are not all the rules how you can define functions. But yeah, so for example, curly braces are missing in the beginning. Yeah, you could have a function call on a type with curly braces. And this is not covered by these cases. You really need to be cautious to cover all the cases. But yeah, otherwise the syntax is super flexible and super powerful. And we can do the same also for the wheres, which you can now compare a bit more directly to the other examples. And we have this call syntax again in different styles and push them to the different where statements. So I hope this kind of gives you an intuition. You have several options, yeah, and they have different styles of how they encapsulate all this logic. And yeah, you have support for really going into the details and matching stuff independently. You have even different options for this. And you usually find good options to kind of parse function objects. But expression parser is kind of really good in having an object orientation access also to other parts of the Julia expression system, like type ranges or arguments, and yeah, a couple of more. Okay, so last part. Oh, I need to be a bit quick on this. So you can also define your own expression parsers. So this is a little example. You find it also in the documentation where you support this traitor syntax. You may have come across this kind of another approach to traits. You have one type information and a second type information bound after another. And yeah, special syntax, which can be supported. And this is just the way you would build it. You have an expression parser macro, which helps you in building this. And, oh, sorry. So this is, okay, now we have it back. And you have kind of a double default syntax, which this supports. So I think this is the key part. If you want to define your own types of these parsers, parsed combinations, this is a helper macro for you. It will define both types on the same run, having the first default argument being the default parser and the second default argument being the default parsed object. And yeah, that's super handy, and all these other types are also defined in this way. And then you just need to define the parse expression and the two expression parts, and then everything is nicely wrapped. And yeah, you just rely on the defined type. Okay, great. So you've seen kind of the general flavor. You've seen a comparison to what other options you have in the ecosystem, how they compare. And you've also seen how you can extend this easily for your own approach. It's really simple, simple approach to parsing and just wrapping it into the semantically meaningful parts, this object orientation. Last, I want to also again point you to cloud.jolin.io, try it out, deployment of Pluto, which I myself really love. It's just there kind of since a couple of months, looking still for testers. You're more than highly welcome to kind of give feedback, but also if you can use it in companies, just reach out. I think Pluto is a perfect way to get started with Julia and also build really complex stuff like streaming online analysis. Okay, that's it from my side. Thank you very much for being there. A couple of contact details. You can reach out to me. I'm here and I will be also there tomorrow for the hackathon. And yeah, thank you. And I think we have some time for questions, only a few, but still.
Okay, great. Any questions? Frames, please.
I think the microphone should go.
Oh, you want to bring it there? I see. Let me see.
Yeah. Okay, that's easy.
I don't really know much about object-oriented programming because I've been writing Julia for so long. Can you tell me what makes this object-oriented? It seems really cool, by the way.
Sorry. So thank you for the question. So it's really a different. So this is all Julia. Yeah. So we are still using multiple dispatch. We don't use inheritance in this kind of object-oriented way. But still, I think it's valuable to think of it in an object-oriented style because you're encapsulating the semantic units really in a type manner, which for me it's rather object-oriented. So to compare what would be functional, the functional is now kind of more, we have the given structures, which we already have, and we now build some complex recursive tools which can work on this seamlessly. So then you construct all your parts kind of by building abstract functions, which then do what you want, instead of kind of defining extra types for the semantic units which are of interest to you. Okay. Thank you for the question.
We have time for maybe one more question.
Hi. Thank you for the talk. I'm just curious if you've done performance measurements or kind of where you see things, and if not, kind of where you see, like what would you expect to be kind of fast and slow in particular in this package?
Yeah, thank you very much for the question. So I was hoping something like this comes up. I haven't done performance benchmarks, and that's because kind of from my point of view of using macros, they are really not performance critical. So yeah, this is why I really went kind of this flexible route, easy to understand package. But I definitely agree there will be some cases where you need performance. I guess it's very rare actually using macros because they will be precompiled anyway. But still, then I would definitely recommend going ML style and ExprParsers Lite. They focus on performance. You just need to do some extra steps to get out some complexities. Yeah, more complex, but you get performance over there. Thank you for the question. Awesome.
Okay, thank you, Stephan. And
thank you again.
It's a great talk, and I look forward to actually trying to use it. So please, let's thank him again.